Good morning, everybody. My name is Ashutosh Garg. I welcome you all to our third session on fired heater design. I work for Furnace Improvements. Our company is in the business of improving performance of fired heaters. We completed 25 years in business last year, so we decided to do this training about what goes on in designing a fired heater. I know most of you are end users or in engineering companies and may have had some exposure to fired heaters, maybe design. But this webinar, which is a 12-part series, we want to talk about what goes on in designing fired heaters, the step-by-step, so that you can understand the importance of a number of parameters. And if you are working on fired heaters or if you are buying fired heaters, hopefully this series will help you. And today we will be covering the most important section of fired heaters, radiant sections. We have devoted 2 sessions. The next session also will be on radiant sections because radiant section is huge. We are trying to cover it in 2 hours. Let us see if we succeed or not. So with that introduction, hold on just. Okay. I think let me see if I can get rid of side panel, hide side panel. Right. Okay. As I said, my name is Ashutosh Garg. I am the founder of Furnace Improvements. I have been working in fired heaters for almost 2/3 of my life. I'm a chemical engineer from IIT Kanpur. Currently, I'm working as a solution provider at Furnace Improvements, providing value-added solutions to our clients. The presentation today has been prepared by my team in Noida, India, and I want to thank them for preparing all the slides and all the materials. I'm just the presenter today. Let me talk a little bit about Furnace Improvements. It's a very different type of heater company. It's not a usual heater company which design, engineer, supplies fired heaters. We took on this challenge of working on existing fired heaters because no heater company wants to get their hands dirty. Fixing old fire heaters is a very dirty business, and we thought, let's take up this challenge. And that's what we have been doing for last 25 years. We have 2 offices. We have a main office in Noida, India now, that's what I call it. And we have an office in Sugar Land, Texas, which is basically our project office, project engineering office. As I said, our main business is improving performance of existing fired heaters. And we work directly with end users and owners. We have a doctor's-patient relationship. And one thing which is very unique with us is we have a contrarian approach. We always challenge the conventional wisdom. And a lot of times we have been very successful, and that's why we have 3 patents today for improving the performance of fired heaters. We also take pride in doing high quality technical work. Because of 2 offices, we are always working around the clock. We can keep schedules. We are supplying heaters currently to a client in about 6 months' time. And we have a policy of do it once, do it right. That's what we do it all the time. So we are a full supply company. We have a process group, we have mechanical and structural group, CFD modeling is also there, and 3D modeling. We produce our own fabrication drawings. So basically, we can do design, engineering, supply, and even erection of fired heaters. That's what we have been doing. We have been revamping projects, and we have been guaranteeing the performance of your existing fired heaters. That's how confident we are of our performance. Uh, I want to take this opportunity to thank all our clients in US. Most of the work, what we do, 90% of the work we do is in US based, although the center of refining is shifting, and we are doing some more work these days in India and other places. But once again, thanks to all the clients and for their trust for the last 25 years that we have been in business. So this is the third webinar, and fire heaters, I don't want to scare you, but they are almost very complicated. So what I mean by complicated is that the first webinar which we did, we spent about 1 hour talking about what information is needed for designing fire heaters. What type of information do you need to provide for design of fire heaters? What fluid you are heating, what are their properties, what is the plot area, what are the environmental considerations, fuel and sulfur content, efficiency content. So there are so many things you need to get it together before we even start designing. So we spent about an hour talking about the major design parameters in our first webinar. Then in the second webinar, we talked about combustion. Combustion is unique to fired heaters. It's the only equipment in the refinery where you can open the PEEP doors and you will be exposed to flames. So we talked about combustion, excess air requirements, fuels. Nowadays, we are lucky to have only fuel gas, but previously we used to have fuel oil. Acid dew point, we talked about a little bit about hydrogen firing, what is going to be the future, what are the factors affecting thermal efficiency, and these type of things. So that's what we talked about in our second webinar. Those of you who missed our first and second webinars, we have these recordings available on YouTube and even on GoToWebinar site. So you can always watch the previous webinars. This. So what we decided to do was to take a real life problem. This is a hot oil heater which we designed for a client in Louisiana about 7 years ago. And this has a very unique design. So that's why I'm presenting it to you over here. I have changed a few parameters to even make it more interesting. But this is a hot oil heater, 126 million BTUs, heating terminal 66 from 480 to 600 degrees. Pressure drop available is about 40 psi. The client wanted 90% efficiency. So the moment you talk about 90% efficiency, you have to give air preheater, especially if they don't want any waste steam. So that's what they wanted. So today we'll be talking about how we sized the radiant section for this hot oil heater. The fuel which we are using for this exercise is not a normal fuel. I just wanted to demonstrate the effect of different components in fuel. So I came up with this composition, which is 25% methane, 25% ethane, 25% ethylene. Ethylene is unusual. And then I put 25% hydrogen. So basically you can see even though the hydrogen is 25% by volume, by weight, it is only 3%. So you can see hydrogen is a very unusual fuel, and we will see, you've already started seeing as people are talking about hydrogen that a lot of unique things will be happening, So same thing what I've done over here is selected a site, El Paso, and the reason I selected El Paso is about 3,500 feet elevation. And the reason, one of the things which affect the fired heater design is the site elevation and also the maximum ambient temperature. So these are the two parameters which uh, control the stack design. And also they affect the burners, they affect the pressure drop. The air is lighter when on higher altitude. So it makes a lot of difference, in the design. You cannot take a heater which is designed for at sea level and then put it at a hill station. We cannot do that. So uh, that's why I selected this. Another reason I selected this was the client wanted 10 ppm NOx and ammonia less than 10 ppm. NOx is oxides of nitrogen, and they are not good for humans. So we want to limit NOx formation. There are two ways we can do ultra low NOx burners, and post combustion is SCR. But for getting 10 ppm NOx, the only way is to put an SCR. So we installed an SCR, and that is another reason I selected this problem, is to show how we installed the SCR. We will cover it later, but I'm just giving you all our design limits. So when we did heat balance in our last webinar, the client wanted an efficiency of about 90%. The inlet fluid temperature is 480. We had different choices of flue gas temperature approach. Flue gas temperature approach means the flue gas leaving the process coils in convection. And we deliberately selected 200 degrees to get a temperature of 680, because at 680 the SCR catalyst has the highest efficiency. At lower temperatures, the efficiency goes down. So we selected a 680 degree temperature for the SCR. And then we installed an air preheater because the client wanted 90% efficiency. So we installed an air preheater and cooled the flue gases to about 365. And as a result, the air temperature goes up from 60 to 435. And we have an air preheater of about 11.3 million BTUs. And the calculated thermal efficiency is about 90.2%. So we did this heat balance last time, simple heat balance. Heat loss we assumed is 2.5% based on API 560. Those of you who don't know what API 560 is, API stands for American Petroleum Institute, and they have the standard 560 for fired heaters for the last more than 30 years. And it's almost like a Bible for fired heaters. Makes a good reading. So here my colleagues have done this combustion products. What will be the firing rate for this heater? We calculated 138.3 million BTUs. Then we calculated what will be the fuel gas flow rate, about 6,455 pounds an hour. We came up with combustion air flow rate, total flue gas flow rate. So we did all these stoichiometric calculations so that we can make the enthalpy curve for the flue gases, and then we can do the heat balance. So this is a very standard exercise we do. So we start with the combustion as one of the first steps for doing fired heaters design. So today we will be sizing the radiant section of this fired heater. We'll talk a little bit about radiant heat transfer, different configurations, single fired, double fired. Then we'll talk about the most important parameter in any fired heater, and that is the average radiant heat flux. We'll talk about vertical cylindrical and box heaters, tube size and number of passes, firebox geometry, burner layout, convection layout. So I think if we can cover these things in the next 40-45 minutes, then we will cover the design example, the actual design calculations in the next webinar. Let us see how far we are able to go, because everything takes time to explain, It's a very important. And those of you who are interested in learning more about radiant heat transfer or how a fired heater is designed, my colleagues have listed some of the references. As you know, Walter Lobo and James Evans, they wrote this paper in 1942, which is even used today, even after 80 years, by all companies. Any fired heater company you go to, they will still be using same correlations, including the FRNC and heater same. So everybody uses the same correlations and makes some minor adjustments. There is a very good paper on fired heaters published by R. and Wim Press, I think back in 1960s. It was published in Hydrocarbon Processing. You can refer that. That also gives you a very simplified method for uh, designing fired heaters. So you can do that. There is a chapter in DQ Khan process heat transfer. That is also very, very useful if you want to go through that, at least the radiant section. And then, as I said, fired heaters for general refinery service. API 560 does not tell you how to design fired heaters. That's one thing. It is more about specifications of fired heaters, how you specify fired heaters, what are the important things you need to specify. That's why we have listed over here. So this is kind of a design references what we have given for you. If you are more than welcome to refer all of them. So today we are talking about the most important component in the fired heater. We are talking about radiant section, where the heat is transferred to the tubes by radiation, predominantly radiation. Typical radiant section absorbs anywhere between 60 to 80% of the total heat duty. This depends on number of factors. And if you are thinking of steam reformers or ethylene crackers, there this number goes down to as low as 40-45%. Radiant tubes are generally spaced at 2 diameter pitch, and they are placed at about 1.5 NPS spacing from the refractory. And the reason for this is what we are processing is hydrocarbon fluids, and to get better heat transfer, we want the back of the tube or the backside fluid to be heated as well. So that is why we place these tubes away from the refractory so that we can get good heat transfer in the back. And we will, if you read a few literature, what we have, this thing, you will understand it very clearly. Uh, very, very basics. I think all of you know, I don't need to put it, but I still thought I will add it. Radiant heat transfer is heat transfer by electromagnetic waves. Radiation always travels in straight line, does not require any medium or any contact. And radiant heat transfer is governed by Stephen-Boltzmann equation, where Q is proportional to T raised to the power 4 of the hot and T raised to the power 4 of the cold. Here, hot will be the flue gases and cold will be the tubes. And we are talking of absolute temperatures in degree Rankine or degree K. That is generally how the relation is described. So radiant heat transfer is very, very important. And let us talk about how the radiation heat transfer takes place in a fired heater. So we have direct radiation. Most of the radiation is the direct radiation from the hot gases to the tubes. We do have, as I said, re-radiation from the refractory walls to the tubes, whatever is going from the gap, and that hits the back of the tube. So that is a re-radiation. And then we have convection from hot gases to the tubes. Approximately about 15% of the total heat transfer in radiant section happens by convection. 85% by radiation, 15% by convection, and that is how the total heat is received. Now, but this heat is received on the outside of the tube. And then we have conduction. We have conduction mode of heat transfer, which is transferring that heat from the outside of the tube to the inside of the tube. And once the tube is heat is transferred to the inside of the tube, now it has to be transferred to the fluid. And fluid gets heated by convection actually. So if you see, even though we are talking of radiation, the conduction and convection play an important role in fired heaters. If the tube is fouled externally or internally, we won't have good heat transfer. If the fluid velocity is low, again, we won't have good heat transfer. So convection, conduction, and radiation, they are all in equilibrium and they all need to be dealt properly and done. When we are designing fire boxes or radiant sections, what are we looking at? We are looking at uniform heat distribution, although in real life, it does not happen. I have not seen a heater where the heat transfer is uniform from top to bottom, but that's what we are aiming for. We are also aiming for good H by D ratio or good H by W ratio. We are looking for good combustion, draft and excess air control, and no flame impingement. We are also making sure that everything gets all flames, all combustion takes place in the radiant section. We don't want any combustion taking place in the convection section. So these are some of the design considerations which go into fired heaters. Now let's talk about how we design radiant sections. So two things. One is all the correlations are empirical. I mean, what it means is it happened first and then they came out with the correlation, And the fired heater design has evolved over the last, I would say, 120 years. I mean, if you look at the old fired heaters, everything used to be there was no radiant section. It always used to be all convection section. And when those heaters started burning out, there was a thought, and that's, I think, around 1940s, they started building a radiant section. So initially it was all convection section. So it's all empirical, and radiant section calculations are iterative actually, that we make certain assumptions and then we check those assumptions. So there are two things which are happening major. One is the radiant heat transfer is taking place, which is based on the flue gas temperature or absolute temperature of flue gas. And second is the heat balance, because once the heat is being absorbed in the radiant section, the flue gas temperature cools down. So what we have to do is to achieve a balance between the two, We want to make sure that the radiant heat transfer and the energy balance is achieved, And we do this, we repeat this process till we get a balance. Now, the funny thing is, when I started my career, there were no calculators, there were no computers, and we would do everything by hand. And it would take 3, 4, 5 days just to even run one set of calculations for a radiant section. Then came computer calculators and things became easier, and then came computers. And now the situation is my engineers can design some of these things in less than an hour because computer speed is so fast that this iteration kind of has become meaningless. They run thing and then they run another. So within 5 minutes, they have converged on the solution. Now the downside is they don't get a feel of the parameters. They just run the simulation and they get the results, but they don't get the feel. So I mean, there is both upside and downside. But radiant heat transfer is iterative. We think that let us design a radiant section, let us do all this calculations of surface and coils and burners, and once that is done, then we will do the heat transfer calculations and see whether we can get a balance, if we are achieving. If we are not getting a balance, we will make adjustments to our radiant section, then again do it. So this iterative process continues till we get a balance. So in radiant section, we can have two types of coils or two types of firing. One type of firing is most common, which is burners in the center, tubes on the wall. And that is called single firing, single fired. And the second one is burners are near the walls and tubes are in the center. And the tubes are getting heated from both the sides. Now there is some advantage when you heat the tubes from both the sides, and that is we can use higher radiant flux, we have lower surface area, lower fluid side pressure drop, lower residence time, and uniform heating of fluid. I mean, if you're thinking about steam methane reformers, ethylene crackers, modern coker heaters, modern hydrocracker heaters, I think they are all generally double fired. The disadvantage of double firing is we have a large firebox, lots of burners, and higher cost. So for most applications, I would say 95% of the applications are the first one, single fired, what we generally you will see in most of your heaters, tubes on the wall and burners in the center. That's some configuration which is mostly possible. This is just to give you some idea. The heat transfer across the furnace, across the tube is not uniform. It is the highest at the place where the flames are seeing the tubes at the front of the tube and lowest at the back. So this circumferential factor defines the average to max ratio. And generally for the normal 2D pitch tubes, the circumferential ratio is 1.8. That means the maximum flux is 1.8 times the average flux. If we increase the spacing to 3D, it goes down to 1.5. And if we do double firing from both sides, then it goes down to 1.2. So you can see we can do double firing and get down to the maximum. Now, what is the significance of maximum flux? Maximum flux defines the maximum film temperature, maximum tube metal temperature, defines the metallurgy, so it defines a number, it basically controls a number of parameters. So it does have some significance, maximum flux normally will, when we're designing it, the users will specify or the licensors will specify that I don't want the flux to be more than 1.8 or 1.5,